All right, folks, welcome back. We'll end today with two important paper readings. These are the great classics that started a lot of the whole generative AI. People often look at these as the milestones. So this paper, I'll give you a little bit of a background on how this paper came about and its history. Um, this paper, well, obviously it is now in V7, but actually it's 2017, December 2017. Holiday season. That's when this paper initially came out. So it's been now 7 years, almost 7 years for this paper. So there's an interesting history. In those days, circa 2017, the key neural architectures that used to exist were, of course, the feed-forward network, the dense net or the linear network that people call, made up of linear layers. It used to be convolutional neural networks. So they would have the concept of convolution, right, which had a inductive bias of locality and so on and so forth. And it was inspired by looking at the way the cat's brain was responding to images. Then there was the recurrent neural network, RNNs, whose mature implementations were LSTMs and GRUs. Those were the reigning architectures in those days, the big architectures. So when people were trying to do a lot of text natural language understanding, natural language processing, they would usually revert to that. And I was just looking back at my notes from 2017 class that I gave on NLP, and I can see all of those. Right? So around that time, Google, obviously, which was very, very concerned with language translation and many of the natural language understanding tasks, it was putting together big programs to create the best models to do some of these. This group of people that you see, it was a collaboration internally created. They all got together. But by the way, none of them apparently are in Google anymore. They have all gone their separate ways. But NVIDIA recently, in their annual event, they brought together all of them. And in the keynote, they had a fireside chat of all of them talking and reminiscing about how it all came about. So this is the paper which started it. And the story is very interesting. The way the title came about is very interesting. What they did is they said, okay, in those days, we had the feed-forward networks, we had the convolutional networks, we had the recurrent networks, and attention had been discovered in 2014. Also at Google at that time. But what people were finding is that if you added attention to CNNs, CNN networks did better. If you added it to RNNs, RNNs did better. But the orthodoxy in those days was that you absolutely need CNNs. And for natural language processing, for text, the orthodoxy was, of course, you definitely needed RNNs. You start with RNNs, and then you decide something else. Are we together? It is like you're sitting down for a Tamil meal. Of course, you need rasam sambar. Then you worry about what else, rice or dosa or idli. Right? It was the orthodoxy. Then these people, obviously, they went with the times, with the zeitgeist, and they created the architecture which had everything. It had feed-forward networks. Well, feed-forward networks, people just sort of assume, they don't mention it. You need it, as you know, for introducing deformations and the appropriate transformations to different dimensions and so on and so forth. So feed-forward networks is given. We won't mention it. They had convolutions, they had recurrence, and they had attention. And they were doing all sorts of natural language tasks like translation, prediction, and so on and so forth. Next sentence, telling whether one sentence follows the other or not, entailment, and all of these things they were looking into very carefully. So they created this big architecture. And then, from what I understand, I hope I get this one right, they started doing ablation studies to see how much was each of the pieces contributing. And what they found is, if you throw away the CNN, performance didn't go down. It was just fine. Right? And then oh, God forbid, what happens if you take the RNN out, the recurrent, the LSTM kind of thinking out, which was the orthodoxy for text? And what they noticed remarkably is that if you throw away RNN, not only it did just as well, it actually did better. And that was a moment of epiphany because RNNs are inherently sequential. If you rewind back to 2017, the computer vision was having really a great time. GPUs were coming out. They could do massive parallelization because convolutions admit to massive parallelizations. And you could do things at scale and very, very fast with the convolutions. But the text guys were having a pretty bad day, sitting there in the sidelines with envy and looking at all these math coprocessors, GPUs, etc., and saying, oh my God, our thing just works sequentially because of the RNN. But the moment you take out RNN, the attention head, the attention unit, it turns out, is inherently parallelizable. In fact, parallelization is not a choice. It is a necessity there. That's how it works. All of the text must go in. The whole text should not go in word by word, one word at a time, but you have to give it the entire sentence or the entire text in one go. That is the nature of attention. And when that happened, many things happened. First, and when you read this paper in hindsight, you notice that clearly the inventors didn't quite realize the importance or the significance of what they were just creating. It was written from a very practical perspective that, look, now we can do massive parallelization. The throughput goes up. And from a computational perspective, many great things happen. Right? In hindsight, when we look at it and people have tried to understand why does all of it work so well. Actually, the understanding of transformers is, to put it mildly, still a work in progress. You build something that works extraordinarily well, and when you scale it up and make massive transformers, as we have today, as all these language models are today, they're transformers. They all use just attention. The real reason, for example, why is a LLM able to reason with you? We have found that it has even a sort of theory of the mind. Before responding to you, it figures out what you're thinking as it responds from your input text, from your prompt. Right? Many, many things we don't quite understand how it does. I would say that with transformers, we really entered a territory which we were entering in AI progressively, from really knowing what is happening to mostly knowing what is happening to now being absolutely mystified why it works so well. Right? It's still work in progress and an area of research. So we will talk about this paper, right? And it forms a backdrop. Today, nobody would have expected, even a few years ago, that there would exist a thing called prompting, and that prompting would write code far better than 99% of the programmers, and far faster. They would not have expected that a prompt would lead to a fairly good medical diagnosis given facts, which does not replace a physician, but certainly smartens the physician up, because physicians in today's culture, they have vast number of patients to process every single day, right? If you have been, for example, to a hospital in India, a typical physician processes 200 to 300 patients a day. Literally in a moment comes up with a diagnosis, listening to the patient, comes up with the assessment, a plan, writes a prescription, and then says next. Right? So you can imagine the value of a machine like this, that sort of you give it as input, the prompt, the history of the patient, the current symptoms, and out it produces a diagnosis. Now, it doesn't mean that you trust the diagnosis, but it certainly means that you have a preliminary sense of what could be. Right? And sometimes it gives you, because the full term for diagnosis is differential diagnosis. It can give you a sort of leading questions, what to do to be sure it is what it is, what test to give, and so on and so forth. So things are moving fast. By no means are these tools perfect, but by every account, they have used the inflection point of utility, namely they are useful. Right? So how does it all start, or what is attention? This paper actually, so now you know where the word attention comes from. Initially, by the way, what was that big network called? It was called CargoNet. For what? Convolutional, right? Attention, recurrent, so car, and go for Google, right? So it was supposed to be CargoNet. And then finally, after throwing about all the words, they realized that attention is all you need. And therefore, the famous title of this paper, right? And then, of course, now it for a little while, this paper was so influential that it became a fad for every, like so many papers to come out that would say X is what is all you need, right? For example, there's a paper called Textbooks is all you need. Right? There's a paper saying something is all else is all you need, and so on and so forth. So it just speaks to how influential this paper was. But for our sake, I'm going to append something. They use the word attention, but technically it is self-attention. Now, I'm going to distinguish between attention and self-attention. It is attention, what they're talking about here, but a special form of attention that is called self-attention. So the question therefore comes, what is attention? Which in this paper isn't quite talked about, because obviously it's meant for researchers by researchers, right? And so this paper has a celebrated equation. All of these diagrams proliferate the web. They have become iconic, right? Just like I suppose the Apple symbol is iconic with consumers these days. In the same way, these pictures, these images are iconic in our AI community. You see them everywhere, right? People I know have hung them on the wall, right? Just to remind themselves of that. And this is the celebrated equation of attention, which again, I will slightly modify and call the self-attention equation. Now, what is attention? I'll give you two definitions of it. First, I'll give you an intuitive definition, and then I'll take that intuitive definition and sort of make it more mathematical, more quantitative. See, one way of looking at it is, imagine that I'm going out hiking, which I do every morning. So I hike from my house to the bay. It's 5 miles down and 5 miles back. After 2 miles, civilization or the human habitation ends, and I get 3 miles of wilderness, where I'm the king of all that I survey. Right? It really feels like that, you know, open skies, it's a bird sanctuary, the water, the bay waters are calling, the marsh. And as I walk there, and the reason I start very early when it is still dark, because for me, an ideal hike is I go out when I can look up, for example, and still see the the Big Dipper, the Saptarishi, or I see in winter the Cassiopeia, and so forth. And then gradually bits of light show up, and I see the whole process of morning happening. I often believe that if you see the whole process every day, it becomes you become somewhat resistant to modern stresses and depressions or anxieties. It does help. I don't know. That's my belief. Anyway, so you're walking there, and then it's dark. Suddenly, you hear. So my mind is at the beautiful dawn that's happening over the hill, the silhouette of the hill. I'm looking at the wonderful fog that has settled upon the creek, on the river. And suddenly I hear, wow. Now, where am I paying attention? Am I still appreciating the beauty of the sky, the fog on the river? No, my eyes are scanning for that mountain lion or that coyote, isn't it? It changes the game. So what it means is, and so what is the difference? Why did my attention change? what was true before and what was true after. Before, I had no sense of danger. I had an open awareness. I was enjoying the nature. But the moment I hear wrong, right, all of a sudden, the context changed. The context is there is imminent danger, isn't it? And my attention is for that thing in the bushes that's about to pounce on me, potentially, isn't it? So, attention, even in normal life, is a concept that is contextual. When we look out at the world, our visual cortex sees a vast plethora of things, of which we pay attention to only a few. That which we pay attention to is contextualized by our current thoughts, our background, right? Our propensities of thoughts, isn't it? Right? Each of us are conditioned differently. For example, if you are a kid who has just learned calculus, you look at the electric wire between two poles and you see the hyperbolic. If you are a musician, your attention is on the music, is on the roar of the cars. You're very sound aware, isn't it? So to each, if you're a real estate person, you ignore all of that and you keep looking at that real estate sale billboard. So our attention is always contextual. That is an important concept. So now let's take this thing, what I just said in an intuitive framework, and let's try to make it much more real. So we are saying that given an input, let us say I have an input which is made up of some vectors, xn, right? Some inputs. It goes into a box. From that box, I need a machine. So you know that if you pass it through a neural network, what will you end up with? The last layer of the neurons, etc., will ultimately produce some output, some voltages, right? So this entire thing will itself be a vector output. Let me call a hidden state vector, right? Made up of H1 all the way to Hn, hidden state value. And something, they all are going through this. Now, suppose I give you a purpose, a goal. Your goal is, let us take a goal and say, given these numbers, or given these things, suppose they are images or whatever it is, which of them represents the largest digit? Now, it's a complex thing. See, if they were just numbers, it was very easy. You would pass it through a softmax function and you would be done. But suppose they are images, handwritten images, right? Something like that. It's a little bit harder problem. I'm saying, figure out which is the biggest of them all, of the digits that I gave you. Now, how would you do that? People have tried to answer this sort of question in many ways. But one of the things, standard convolutional networks, et cetera, with some degree of success, they have tried to do that. Even a humble feed-forward network has pretty good success rate. Now, you realize that this problem is not a problem of recognizing a single digit. That is easy. You give an image, handwriting recognition, MNIST. It's a little bit more complicated. One of the things you could do is, you could say, what do digits look like in general? Right? And compare each digit to that in some sense. So in other words, somehow, if you could create a context vector and then convert every I to the context, how aligned that I is to context. Let us say that somehow the context vector was such that the big numbers were making positive angle, the lesser numbers were making negative angle, sort of negative angle. So if you look at the cosine or the dot product, you would get positive or negative values. The more positive, the bigger it probably is. Right? Suppose you could do that to a machine, and we can always do that with backprop and training and so on and so forth. Then all it means is it becomes easier for me to know which is the biggest of this, which image represents the biggest picture. I just look for the most alignment. Like I pay most attention. In other words, to the most aligned, the most this is the one that this thing I should start paying most attention to the one that has the biggest, let's say, dot product. Does this make sense? Let's give it to something with the highest dot product. So that becomes attention. And all I need to do is figure out which of these images should I pay most attention to, because that attention will be pointing to the biggest of them all. Right? That's the context of attention. Now, the thing is, it requires you to take the totality of all of the inputs and create a context from it. Now, I'm not going into the very specifics here. Right? We'll keep that for the other neural networks class, where we go into it much more. But this is the main idea. Attention is alignment to context. Taking it back to the intuitive space, when I'm for the roar of an animal, my attention should be on that object, which really is about animals, right? Is a dangerous animal out there somehow, right? So that is what attention is. This concept of attention for vector and its alignment to a context is attention. Technical definition of attention. So this was the work in 2014. Then came this paper, and what this paper says is quite remarkable. It said that, see, suppose you were to take a machine and we will call it an attention head, literally that. Take the word, the cow jumped over the moon. Now, in recurrent neural networks, you would give the machine the word one at a time. But now you say give it all at one go. And then do one thing. Why do you want to give it all at one go? Because from that we can extract the attention, in a way, a sense of the attention. And now what you do is treat each word and ask, how much attention should I pay to other words? Right? So for example, suppose cow is the word, right? What it can do is that you create an attention equation, attention for the cow, how much attention it's paying to the cow. What it should do is that it should pay a certain degree of attention, let me call this vector. So for reasons, I will use sloppy language and then I'll smarten it up. Cow, right, to some form of attention. I will put the word K, but that's cheating because I'm looking ahead a little bit. But just think some context, right? Because that's what we were doing aligning it to context, right? I'm just from C, I went to K. Sounds familiar, similar. I'm sorry. So Germans would say, yeah, good idea to replace C with K. So this is the attention that the cow pays to this, right? Now, but every K, the K is actually associated with every word, I. And so what you do is you, actually, let me call it Q because this is what the books, the paper will say. The cow is the word, the reference word. And we are trying to figure out where is it paying attention to. Now, where in mathematics always means a vector. So what it will mean is, it will have, if it is paying all its attention to moon, it will be pointing in the direction of the moon, isn't it? But it might be paying a little bit of attention to jumped. It might be paying some attention to that. So it will be the superposition, it will be the accumulated attention from the different things. And so what they do is you take this is called the attention score. So this much attention it is paying to, let us say, the actual value of I. And this needs, why did I break up the words into two parts, Ki and Vi? For a reason. We'll come to that. This reason is somewhat understood, but we'll come to that. But you're saying that if it is the moon, so for example, a cow is paying some attention to the K of the moon, and here just say it's context, and that much, and therefore, based on how much score it is, that much it is weightage or importance it is giving to the moon vector. Are we together? But that's not the only thing there. It might also be paying a little bit of attention to jumped vector. K jumped, V jumped, right? This is the score. By the way, I'm deliberately I'm just sort of wiping out some technicalities because let's get to the intuitive idea first. So far, are you making sure? And plus somewhat all the other words. And as you can imagine, if the cow, if you have to translate this, let us say into French, or let's say Tamil or something, you can't do word-to-word translation. That would be junk. What you need to do is the words in any other language would have a completely different order, and it would have different number of words and so on and so forth. So what you do is you create something called a hidden state, language representation, right? And so that brings us to the concept of a language model. We'll come to that. Now, you notice that the only difference between me just talking about the context here and this new formalism is I somehow broke up the context into K, Q, and V. Why it makes sense, and this paper does that. When you do it like that, it becomes self-attention. Why it does like that? I'll give you the sort of hand-waving argument that everybody gives, though many researchers are not happy with it. They feel that it's all very hand-wavy, and just because it works doesn't mean you understand it, right? So think of it like this. And for Google, it was sort of intuitive because they were in the search domain. So a very simplified picture of search is this. You will have, let's say that I have a document, many documents, where, think of URLs, right? D1, DK. What do? You take the sentence, the cow jumped over the moon. The happy cow was grazing in the meadow. The kids were happily playing. In its very simplistic core part, a search engine is this. It's a hash table. You have a keyword, right? So for example, the keywords are here, jumped, moon. You remove some of the top words or the common words, right? So what can you do? You can say that, for example, the word cow is there in document 1. It's there in document, this is D2, D1, D2, isn't it? The word happy or its variants is there in D2 and DK. Right? The word kid is there in DK, so forth. So suppose you are searching. This is called an inverted index. So notice that what you're saying is every document has a key that points to its location, isn't it? And the document itself is the value in some sense, isn't it? So, because a hash table is key value, right? KV. Now, suppose you have a query, a user gives a query, and the query says, let's say cow. Well, you have a direct hit. All you need to do is go here and you look it up, right? In a way, the query just needs to pay attention to the first row, be aligned to the first row. Does it make sense? Now, if you say happy cow, then you need attention here and here. You go and retrieve both of them. They have pretty high attention, but you ignore the other ones. If you said happy kids, then you would take the next two, right? So again, what are you doing? You have a key and a value, and if you were to think of it, so now this is a hash table. But machine learning deals with differentiable functions and vector spaces. So how do we now take the intuitive leap from what is just a hash table to this? So let's make it fuzzy, right? From discrete to continuum. Suppose the word was, let me think of a word, child. Oh boy. Intuitively, what would you do? You would ask, how aligned is this word Q, child, to all the entries in the hash table? Does that make sense? And you would therefore conclude that, oh boy, I need to pay far more attention to kid, right? Child, well, maybe a little bit because even cows have kids, calf, right? But maybe the other word that may be sitting there, moon, is not terribly relevant, right? And not quite irrelevant because children do look at the moon, but primary importance, it should be far more aligned to child. Am I making sense? And so now, how do we do that alignment? So what you can do is, what if everything, this was a vector, value itself could somehow be encoded as a vector, and your query was a vector. Now it is easy. You would say, I'm far more aligned, Q is far more aligned to the K of child, kid. Q, so what was the thing? Q was child. It is far more aligned to the key kid. By the way, this is my weird way of writing dot products because dots are a little bit hard to see. But would you agree that this should have bigger score? And so I should pick the value dk with that much more emphasis, isn't it? So I should therefore pick value of kid much more than I would pick the value of, let's say, cow. But little bit contribution comes from everywhere. And therefore, that is the intuition. That's the core intuition of using three things. A query in a way becomes the main context. What are you looking for, right? You may have a sentence, pay attention to others, it becomes the context. I am paying attention to something. What, right? And then you have this formalism of information retrieval, KQV. Now, does the word KQV make sense? So now how does the paper go about it? See, guys, if you understand this basic intuition, that this is the attention that child pays to the kid, is the attention score. This is the attention. But then if you want to have the full child attention, how much you should return, you would agree that you should sum over all the other words, right? Q child, KI, VI in this system. Would you agree with that? You would want to do the dot product and get those scores. And then you would get the A vector, which says, hey, in your search results, primarily pick this guy up. And then a little bit of happiness also talks about children, go for it, or something like that, right? So you would do like that. Now, what this paper does, it takes that intuition and says that what if we could take the word, the cow jumped over the moon, do this, pass it through a machine, each word, it gets broken. So the thing is, words don't enter machines. Machines only take vectors. AI models only take vectors. So how do you convert a word to a vector? There are two ways. There were technologies like word2vec, etc., but don't. What you can do is, okay, so you use some formalism, but what you do is, first you have a vocabulary which contains all this thing. One, maybe the word aard walk. Those of you who took GRE would remember it. You start memorizing the dictionary with aardvark, right? And maybe there is some word here, 10,000 or 30,000, which says Zephyr. I don't know. I don't know which is the last word. Something like this. Does that make sense? And then, so each of these, each word, therefore, can be associated with a number, an ID. So and what you call is, this is the vocabulary. A word must belong to the vocabulary. But then what if you encounter a word not in the vocabulary? English language has millions of words. So unknown, you need to keep a special token for unknown and so on and so forth. If you don't find it, give it that ID, right? And it seems to work. So vocabularies these days are 30,000, a million, whatnot, right? You take a fixed vocabulary, get an ID. Once you get the ID, then you apply a little bit of a magic. And I'll tell you, the old way used to be use things like word2vec or there's that. There were technologies to associate a vector with each word. The point of a vector is that two words, which are very similar in meaning, would be aligned. But this new architecture turns it on its head. It says, okay, let that embedding itself be discovered, right? But just say that for the time being, just think that each of these becomes a vector, EI. Now comes a problem. Something comes out of this. Here, right at the entrance, there is a little bit of a problem. If I send all the words together, now, how do I remember which word came before which? Isn't it? When I sent it through a recurrent network, one word at a time, order is implicit. Isn't it? So, for example, if I say, no, I did go, versus, no, I did not go. You see that the order completely inverts the meaning. So order is important of the words, right? Very obviously. But where is the order if I throw in all the words together through a network? So what you do is you add a position vector, something that induces the position of that word into the vector. So you create a joint vector, position plus the word embedding vector, and you create a joint vector. Now you've passed that into the network. And what you do is you break each vector into a K, Q, V. So K1, Q1, V1, K2, the cow becomes, so let me take the cow as an example. K cow, V cow, Q cow. Why? A cow, a K and V make sense. It's almost like you're thinking hash tables, except that a vector version of a hash table, right? What used to be a lookup table, the keys have become vectors in a vector space, D-dimensional. By the way, you typically take D in the original paper as 64-dimensional. It became a vector in 64-dimension, but the intuition is still you're thinking hash tables, right? But now into a more differentiable continuum space. V also makes sense. V is basically the cow, right? But what about Q? Where did that come from? Because and this is the self-attention. Every word is in effect a context that's asking, who do I pay attention to? If I am looking around into the sentence. So in a way, I mean, see, there are broadly different ways of looking at it. You can say that the whole sentence is the context in some sense, right? It's contextualized. The cow is contextualized by the sentence, isn't it? So the cow, what attention it needs to pay comes from, now you can say the attention vector of the cow, therefore, will come from the query of the cow. So you take the query vector of the cow. You say, okay, the key and the value we keep separately. But when it goes probing for who to pay attention to, we'll deliberately keep a separate vector. Now, obviously, you notice that I'm getting a little bit hand wavy here, but it is the nature of it. People like Anthropic actually have tried to reinterpret the paper in a much more rigorous, mathematically rigorous, interpretable way, but we'll leave that aside for now. So this query vector pays a certain degree of attention, or it is like looking up the, let's say the word moon, value of moon, plus all the other ones, right? The differential attention. So this is the score. So this equation you can think of as the attention vector for cow is basically the score of moon times the v moon plus all the other words, right? How much the dot product of cow is, including dot product with itself. This is your attention. Now, so now with that, let us compare that to an equation that is here in this paper. Now, please pay attention to this most celebrated paper. Does this somehow look somewhat familiar? Right? What is QK transpose? It is a matrix notation for dot product, right? It's just matricized everything. So I glossed over some detail and then you multiplied by value. Now I glossed over something. It turns out that for computational efficiency, it is a good idea to divide it by square root of the dimension. 64 dimension, for example, will become 8. Just empirical observation. So you stick that in. Right? It has no deeper meaning. Oh, softmax, where did that sneak up on us? See, softmax comes from the fact that when you do the scores, you want all the scores to add up to 1. You say that, okay, 80% here, 20%, 16% there, 4% here, and so forth. So when you get a bunch of these scores, to normalize them such that they all add up to 1, the easy trick for any bunch of numbers is softmax. So if I take softmax, so this is a digression into softmax, take any bunch of numbers, pick a number, let's say -10 to, anybody else? Any number? 7. Okay, we'll just take 3. See what happens. What does softmax do? Softmax is, for each of these, exponentiate it, e to the -10, e to the 2, e to the 7. Right? Then divide each of them by the total. So what is the total? Sigma is, well, what is e to the -10? Approximately. 0? 0, right? E square would be approximately, say, 8, give or take. E to the 7 is pretty large number, let's just say, right? It is 64 times 8 times 2, 64 times 16, right? 64 times 16 is approximately, let's say, 1,000. I would venture in the order of 1,000. So when you sigma it all, would it be reasonable to say it is basically dominated by this value, right? And so what will happen when you softmax it, in other words, divide all of these numbers by sigma, you will end up with practically 0, 8 over 1,008, and 1,000 over 1,008. But observe something, they have all become positive, right? And therefore, you can treat them as probability because they also take values between 0 and 1. You can reinterpret anything coming out of soft. So what happens therefore is you can think of the score as what is the, not just the degree, the score or degree of attention you're paying to it, as sort of like a probability. But here the probability meaning doesn't make sense. But in, as you know, in classifiers, that's how you treat them, probability. Yeah. So that's why you use softmax. So that's how softmax crept up on us, right? So it doesn't add sort of conceptual meaning, but it is a good thing to do. It prevents numbers from blowing up and many good things from happening. It just is a good thing. So you just softmax it. When you do this, now you know what attention does, right? So now a little bit a different concept comes in. I will just tell you, we keep speaking of language models, right? So anyway, before I go to language, let me close the chapter. So guys, do you understand what self-attention is now? Given a text, you can push it parallelly. Each word will pay attention to other words. For each word, therefore, we'll have an attention vector of how aligned it is with the values of the other words, isn't it? And it is sort of a generalization, continuum generalization, a vector calculus generalization of the humble hash table in some sense, right? From an information retrieval perspective. Very hand wavy, but let's go with that. Now let's come to the concept of a language model. So when we say a language model, these days it's very, every person knows what a LLM is, a large language. So let's deconstruct large language. Large is it's an adjective, and it's a matter of degrees. What was, for example, big data? What was big data yesterday, 10 years ago, looks like something you can fit into a laptop. Perhaps not a laptop, but at least a workstation these days, right? As you start having even machines with 100 terabytes and so on and so forth, easily, nowadays, the old-time big data, or one Peter, begins to fit into one workstation or one NAS. So big data is relative. Big is relative. We just mean data at scale. In the same way, large is relative. What was large yesterday looks really small today, right? We'll leave that as we saw in the presentation just now. Llama 3.1b is a massive model, was trained on trillions of tokens, took $120 million of compute time to just get trained. That these days, just the sheer economics of it and the scale of the weights we consider large, though already people are dreaming up and cooking up models that are 10x the size. Right? It's a continuous race. So we'll ignore the word large. Let's therefore, from the LLM, large language model, let's focus on only the word language model, because this is there to stay. What is language model? And by the way, many researchers, they specifically prefer to only use the word language model. Right? So when you see the word language model, remember that they're talking about the same old LLM, right? Large language model. So the question is, what is now there's a subtle distinction. The way LLMs are meant in popular imagination is often generators of tokens. But the way language models are meant in the more sort of a strictly engineering perspective is slightly different. So I will tell you what a language model is from a more serious perspective. A language model does this. So suppose you give it some text. And suppose the task is, I need to convert the text into, let's say, French or Tamil. Now, what happens is this text goes in. What you expect is English, let's say, and then let us say a French text comes out. You would agree that the words would not be in the same order. Right? So how would it do that? A little bit of thinking would tell you it's exactly how interpreters do. What do? They hear, if you have an interpreter translating a lecture as it is being delivered, as spoken, and diplomats tend to have those interpreters as they talk to people of other languages, other nations. The person says something, the interpreter understands it, and then translates it into another language. So if you look more carefully, what the interpreter did is took the text, English text, interpreter, this person, came up with a mental idea of what did the speaker say. Right? It has a mental representation. If you think about it, you don't immediately start translating. You wait to understand what the person has said, and then you translate. So you come up with a hidden representation, a latent representation. And then let us say that the interpreter can translate into 5 languages. But today, she is interpreting it in French. Right? So, oh, I'm sorry, I keep making mistakes with this. Okay. And so you need then, this is the encoding part of it, encoder. Interpreter at that moment, the mind of the interpreter acts as an encoder or understander, understanding machine. It encodes it into a full representation. Then you have a decoding process. It says, okay, now how do I say it in French? Right? You go through the decoding process. So there's a decoder. And will come out, let's say French. But see, from the latent representation, the same interpreter then might turn to another person and say the same thing now, let's say in Tamil. Do you see that, right? So given a latent representation, one decoder can do it one way, another decoder may produce or some other thing. Do you get that? This latent representation is synonymous with a language model. When you give it a text, the internal representation that it creates is a language model. And therefore, neural networks that are capable of forming a representation of text in itself are language models. So the word is more widely used. So that's the way to connect the dots from the way we think about it here and the way popular imagination has caught up with it. Now, observe the fact that when you have a latent representation, translation is not the only thing you can do. I can take the latent representation. Let us say everything in machine learning is either a vector or a bunch of vectors, right? H1, HK. I can take this and feed it into a classifier, for example, and just say decode whether the person is angry, sad, happy. I could do a classification for it. I could do a decoder which answers a different question, which says summarize it. Right? This is way too verbose, summarize it. Or I could say rewrite it in Shakespearean English. Isn't it? So the point is that once you have a language model, you could decode text into a whole variety of tasks. Some of the common things are, for example, and the first text generation, this also leaves the potential to ask an interesting question, not just translate, not just do this, but suppose I ask it the thing, what decode it into what you think the next sentence should be. Right? What am I doing? I'm asking you to do a continuation. Are we together? I'm saying, here is sentence 1. You go through your entire process of encoder, representation, decoder, but whatever you do, at the end of it, tell me, give me an S2, which most human beings will say, yes, it's a continuation of S1. And while you're at it, continue S3, S4, because I can keep feeding this back, right? I can keep feeding it back in a loop and say, okay, what comes after S3? What comes after S4? Right? And therefore, do you see, you just created what is in, like you're seeing generative model, you're staring at a generative model, isn't it? And in a way, you could say that, see, decoding is inherently generative. When from English text representation, you're creating French, that was generative. When you summarize a text, that is generative. So today, the way we look at it is any model that has a decoder, generally we consider a generative model, right? So it must. So now this, what happens is, this paper, now let's go back at it. What it is saying is that this technology, the thing that does this kind of math, is called an attention head. Attention head is that bit of neural circuitry that will help you do this, right? First split it out into KQV, then do the attention thing. Now, if you get the gist of that, now let's start by looking at this image. What is this doing? You multiply K by Q, matrix multiplication, scale it, square root of D. So you remember this is K, a Q dot K. In my notation, it is this. What is this? This is dividing it by the square root of D in the equation. This part here, square root of D, isn't it? Why do we do that? It's a practical consideration. And then mask, ignore the mask, we'll come to it later. Then you softmax the whole thing. Why do we softmax? Just to normalize the scores. And then you multiply it by V, right? So this is just an equation that expresses this. Does that make sense? But here comes something very interesting. In engineering, people always believe that if something is good, more is better, right? So you see that if attention is giving you good results, how can you amplify the effect, right? It's somewhat like if you have one bulb giving you light, how do you really have a well-lit room? You would say, well, light up lots of bulbs, isn't it? Go about lighting up lots of bulbs. So when you have this neural circuitry, the question is, how would you create lots of bulbs, sort of attention heads? So what you do is, there are only two choices you have. Think about it. You have a text going in, and I'll draw it in the traditional way. Text will go in. It will go into, let's say that it was going into one attention head. What you could do is, the output that comes from this attention head, treat it as though it's input. Why not create a tower of those attention heads? Are we together? Keep feeding it in more and more attention, because we know experience from CNN is one layer of convolution good, many layers better, right? So in the same intuition, one attention head, well, they pass it to the next attention head. And while you're at it, they realize that, okay, so you created one tower here. This is practically one tower, attention head tower in some sense. You do that. While you're at it, why not create more towers in parallel? So this text goes to this, to this, to this, and here there are more towers. And the way you do that is, you actually don't do it the way I've written. You cut it out. You think of it like that. And you say that at each layer, the output of the previous layer is going through many attentions, isn't it? Many attention heads. Now, the reason this got interesting is, or they found, putting many layers makes common sense, right? Whatever one layer would do, many layers would do better. But why this horizontal split? Why so many of these in parallel? Why am I sending the text, same text, through different attention? Won't they all learn exactly the same thing when you train a neural network through backpropagation? And this is where the magic comes in. See, guys, when you do supervised learning on a neural network, it's trying to do some task better. To do the task, it will surely realize that if all the, let's say A, B, C, D, if all the weights in A block, B head, C head, and D head, they were identical and they were doing identical tasks, it is redundancy and they are not getting the benefit of numbers. So you do what, for example, common sense people would do. You say, you get better at this and you get better at this. And the collaborative effect will do the whole task better. And that's literally what happens. The sheer pressure of backpropagation and of the errors and gradient descent of learning causes the A to perhaps focus more on the grammatical aspects, B, to perhaps focus on some other linguistic feature of the text, and they sort of specialize, and they are looking at the same text from different perspectives. But that is multi-head. When you do that, you say, this was one attention head, now this is multi-head attention. Does this make sense, guys? And that is what is represented now. So this paper, it's one of those papers that you don't get a lot of explanation in it. It's written very much from a practical perspective. But I hope I gave you some intuition now. Do you see that multiple copies are stacked one behind the other? Like the same signal will go through many of them. It is here, it's multi-head attention. So now let's get back to our bigger picture. What is this? I said that the basic architecture has to be that text goes in, it creates a hidden representation, latent. It produces a latent representation, which goes into, now I'll deliberately cheat and make the decoder the way I made it, decoder, and that produces the output. Isn't it? This is exactly the encoder, decoder. Do you see the parallel here? So here, what is the encoder? Encoder. What is the decoder? Decoder. Remember, decoder is autoregressive. What does that mean? Means if it produces a word, let's say that you have a box and it produced the word the cow. Before it produces the word jumped, let's say that you gave it French text and it is producing English out of the French. It so far produced these two. What you want to make sure is not only the latent goes in, latent representation goes in, but you have to also give the additional context back, right? Otherwise, if you just keep on giving nothing but the latent, it will keep saying the, isn't it? But the moment you give it cow also, now it will say, okay, given the and the latent, I better say cow. Does it make sense? So this is the autoregressive loop that you have to go through. So decoders always have that, right? So this is it. Now with that, if you look at this paper, it's a dense paper. I will read the introduction to this paper and say the dominant sequence transduction model. What is transduction? English went in, French came out. Right? So it's not just conductance, the same thing goes in and out. Transduction, there's some transformation in the passage of it. The dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and the decoder. See guys, language models definition is that, right? And here the word sequence transduction model is the same as language model, right? It has an encoder and decoder. And at the time of this writing, they used to be made up of convolutionals or recurrents. The best performing models also connect the encoder and decoder through an attention mechanism. In other words, people had realized that if you built it out of RNN and CNNs, throw in attention, it does better, right? That's the second sentence. Next comes the main thing. We propose a new simple architecture, the transformer, they called it, right? So based solely on attention mechanism, dispensing with recurrence and convolutions entirely. That is a shocking statement, right? That was the epiphany. That good grief, how can you throw away the recurrence? Right? Well, okay, if you don't use recurrence, then at least use CNN. Oh no, neither of the two. Then how will you do it? And what they are saying, attention is enough. Experiments on two machine translation tasks show these models to be superior in quality while also more parallelizable and requiring significantly less time to train. You know, when something like this happens, it not only performs well, but it also, as a machine learning model performance, but also in compute time, performance goes up. Both of them, that's remarkable. And so the rest of it is they show blah, blah, blah. We could do blah, blah, blah. We'll ignore all the blah, blahs. Right. And I hope I've given you the background to this paper and mostly explain this paper to you. Right. I invite you to go read this paper, and you will get it. The interesting thing is, look at the results. Look at the results. Blue is a benchmark, right, for translations, English to German, English to French, and so on and so forth. And look at English to German translation. Usually when a research breakthrough happens, it underperforms the state of the art. You need a lot of fine-tuning to get better. But right off the bat, if you look at this screen, it has beaten the state of the art. Likewise, English to French, it has beaten state of the art. And you realize that it does that remarkably less expensively than the ConvNets and the other very complicated mixtures that people had created at that time, right? So that is the main result of this. They try it out, and so the common NLP tasks are machine translations. It does very well. We just saw there are variations, etc. So they're hyperparameters. They change it and they play with it, and they see what happens. And that is it, the conclusion. So let's read the conclusion. In this work, we presented the transformer, the first sequence transaction model, based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architectures with multi-head attention, right? And blah, blah, blah. That is it. I hope you understood, at least at the core conceptual level, the landmark paper that has started all of this these days, right? So let's take a 5-minute break, and then we'll go to the next paper. And that will be the last activity of the day.
Asif, would you mind? I posted a couple of links in the chat. It's a little simulation for attention mechanism if you want to show it for intuition.
Oh, definitely. Actually, would you mind please posting it to Discord? I'll add it to the course page.
Okay, I have 4 posts actually there.
Okay, then all 4. I would love to show all of them to people. Should I show it right now?
There is one that would be great, actually. The first one.
Okay.
First
there we
one,
go.
Visualization.
This is it. Is this the one? Okay,
oh,
this is it.
Yeah, this is one. The next one is even better, actually.
Okay. Let's
Yeah,
bring
you
the next
can
one
basically expand that, make it a full screen. If you go into that video, if you could make it a full screen.
Yeah, I will do that. And of course, I'm going to also post. Oh, yeah, this is exactly the one that is already posted on the course portal. You remember ML1, LLM1, LLM2? This is the 3 blue, 1 brown.
Yeah.
This is the 3 blue, 1 brown, right?
Yeah, yes. The next one is actually interesting, but I think you're still on record, by the way.
I'm still on record. Okay, let me